Next is residual analysis for influential observations. An observation is said to be influential if it has a strong influence upon the regression results. If there is just one or two points that affect the regression coefficients, then such observations are called influential observations. So for example, let's look at this plot. Okay, here most of the points are here, and there is one point which is way out here on the x-axis. If you drop this point, then the regression line will be positively sloped going this way. Just the presence of this one value, so such a high x value, now changes the direction of the regression line to negatively sloped line. So you can say that this point has a very high leverage on the regression analysis. So this is an influential observation. And how much influence each point has on the regression can be calculated by what is called a leverage. The leverage is the amount of influence, a measure of influence upon the regression results. So H sub I is the leverage for each observation. So this is the formula that we use. And if H sub I is greater than 6 over n, where n is the number of observations, or 0.99, whichever is smaller, then that observation is considered high leverage point. So in these cases, what can we do? Well, if the observation is not valid, in case there is a typo or some kind of recording error, then we can correct that recording error and find new estimates for regression equation. If not, if it is a valid point, then we need to collect additional sample data that covers these intermediate x values. So if we have enough points that cover all the x range, okay, with not so much of a gap, then we will be able to develop more accurate regression coefficients. So let's look at an Excel example now. This is the data from the textbook, table 14.2. So we have the x here and the y here. So let's first plot a scatter plot and examine the scatter plot. Now let's clean up the format and move it down here. Now when you examine the scatter plot, you see that most of the points are here, and there is one point with a large x value, and this is likely to be a high influence point. Now let's calculate the H sub I values and then see what, whether that particular point is a high leverage point or not. So for that we need x bar. So that's the average, and we need sum of x minus x bar squared, and we can calculate that using DEVSQ function. So this will give us, this function will give us x minus x bar squared sum. N is count. Now 1 over n. The critical H sub I is the smaller of 6 over n and 0.99. So this is the critical H sub I. Now let's construct the H sub I's. The formula for H sub I is so we need x sub I minus x bar squared for individual observations. So that will be x sub I minus x bar, that should be absolute referenced, squared and h sub I is 1 over n. We've already calculated 1 over n here, absolute reference that, plus x sub I minus x bar squared divided by that, and absolute reference that as well. So that will give us the leverage value for h sub I. Copy that. Now we can set up a formula for identifying high leverage points with an if function. So if h sub I is greater than the critical h sub I, absolute reference that. If that is so, then this is a leverage observations. Otherwise, it is not. And let's put a hyphen for it's not a leverage point. Copy that. So now you see the last point is a high leverage point because h sub I exceeds the critical value. So and that's this one. So when you have a high leverage point, you need to check whether there is a typographical error here. Maybe it is not 70, it is probably 7 or something. If that is so, you correct it. Otherwise, you have to gather sample observations with x equal to like 35, 40, 50, 60 and so on. Fill up this gap. Then you will not have the high leverage problem.